Hello, and welcome to the first lesson in Module 9, 9.1. This is Exponential Functions. Our objective for today is that I can recognize situations modeled by linear or exponential functions, and I can graph exponential functions showing intercepts and end behavior. So, our vocabulary. An exponential function is a function in the form y equals a times b to the x, where a is not equal to 0, b is greater than 1, and b is not equal to 1. So what do we have here? Exponential growth functions where we are growing, something is getting bigger and bigger and bigger. We have an a value that's greater than 0, so our first term is positive, and we have a b value that is greater than 1. So the thing that we are starting with is positive, and then every single time we increase our x variable, we are multiplying by a positive greater than 1 number. So that means it's going to get bigger every single time. An exponential decay function, a is still going to be greater than 0, so our first term is still positive. We're still taking some quantity, and we are multiplying it by something that is less than 1. So we are multiplying it by a fraction, a decimal. Think in terms of like 0.5, 1/2, right? We are multiplying by 1/2 over and over and over again. So we are breaking apart. We're getting smaller after each interval. And there's a new vocabulary word for us here that you probably haven't seen, and it's asymptote. And this is the line that the graph of an exponential function approaches. So we're going to look at some examples, but first let's deal with that first part of our objective, identifying exponential behavior. So when we have data in a table, we can look at, we've got two functions here. We've got what is the difference between y equals 2x and y equals 2 to the x power. It's an exponential equation. Our variable is in the exponent. So we are going to see what happens. So if we have 2 times x, 2 times 0 is 0. 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 8. So if I look at my rate of change, going all the way back into modules 1, 2, and 3, so our x values are increasing by 1 each time. Our y values are increasing by 2 each time. So our rate of change is 2 over 1, which is constant. Now, if we look at the rate of change for an exponential function, so 2 to the 0 power, anything to the 0 power is 1. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8. 2 to the fourth power is 16. So if we take that same approach, we look to see what our increase is. So we're adding 1 for each time on our x value. And our y value, we're adding 1, we're adding 2, we're adding 4, we're adding 8. Well, that doesn't seem right. So it's not constant, right? But what is happening? Instead of looking at it as a addition, what are we doing each step? We're multiplying by 2. We're multiplying by 2. Multiply by 2. Multiply by 2. So this is, our pattern is that we are multiplying by 2. So it is not a constant relationship. And when we start to graph these, you'll see what I mean when they're not constant. All right, letters A, B, C, and D are you-try problems. I would like you to do those now and check your work against mine. So if we zoom in on letter A and B here, so letter A, our x values go up by 1 each time, and our y values, we go up by, we go up by 2, we go up by 6, we go up by 18, and we go up by a lot. That's what's 58. So, but what do we really need to worry about here? What's actually happening as we take each one of those steps? What's happening is we are multiplying by 3 each step. So what type of equation is this one? This is exponential. Okay, let's look at letter B. X values, we are increasing by 1 each time. What's happening to our Y values? Well, as we go, it looks like we're adding 6, we're adding 6, adding 6, adding 6. So each step we're adding, this is linear. Every step we add 6. Letter C, what's happening here? Again, our X values are all increasing by 1. But what's happening to our Y values? Well, to go from 1/4 to 4, multiply by 4. To go from 1 to 4, we multiply by 4. Multiply by 4. Multiply by 4. So this is exponential. And when we go to letter D, again, our X values, we are adding 1 each time. And what's happening is we're not multiplying. Well, we are multiplying. Do we know what we're multiplying by to go from 25 to 5? You might not see it right away, but what you should see is that that's dividing by 5. Or our alternative way of thinking of that would be multiplying by 1/5. Okay, so each step we're multiplying by 1/5, by 1 over 5. So this is the difference between an exponential growth and an exponential decay. An exponential growth, your Y values are getting bigger and bigger and bigger as time goes on. Your exponential decay, your Y values are getting smaller each time. So letter D is exponential. All right, let's go to page number 2. Now, page number 2, there's not a whole lot that we're going to write on here. We're just going to talk about what is the difference between exponential growth and exponential decay equations. So first of all, if it is growth, we have b to the x, where b is greater than 0 but not equal to 1. So an example of that is y equals 2x, or 2 to the x power. Exponential decay, y is equal to b to the x again, but b is going to be between 0 and 1, but not equal to 1. So something like 1/2 to the x power is an example that we're going to look at. Our domain and range. The domain is our set of possible x values. Our inputs. Okay. Our range is our possible y values. Our outputs. So the domain on both of these would be all real numbers, and our range is going to be, both are going to be greater than 0. And we're going to look at why that is. So again, asymptote comes back up. This is going to be a line that a graph approaches. Each one of these equations is going to approach the line y equals 0. End behavior. What is happening as we go towards infinity in each direction on our graph? So we did a little bit of this where we were talking about end behavior on linear equations, and I think we dealt with some quadratics and just some kind of weird functions where it was going in different directions, so different pieces had different relationships. So in the specific case of an exponential equation, as x values decrease, or approach negative infinity, what do the y values do? What are the y values doing as your x values get smaller and smaller and smaller and closer to negative infinity? Okay. And then the second part is, what do the x values do when they increase? When they increase, as they're approaching positive infinity, what do the y values do? So as x gets further and further to the left, what's happening? As x goes further and further to the right, what's happening? It's going to have one of two things. It's going to approach your asymptote, or it's going to increase or decrease to infinity. Okay? So in the case of our graph on our left, as the graph goes towards negative infinity, as the graph goes this way, it approaches the line, it approaches zero, right? And as x goes to positive infinity, x increases and y increases. So y also goes to infinity. Okay? Now, on an exponential decay equation, right? So this is one that has a fraction less than 1 as the base. We have as x increases, so as we go towards, actually, no, we start with decrease. So as x decreases, as our x values go to the left, what's happening? Our y value is increasing to infinity. As our y value or x values go towards positive infinity, we are approaching zero. Okay. These are our two graphs of an exponential equation. Exponential growth on the left, exponential decay on the right. All right, now let's look at some examples. So we're given this first one that the exponential growth, it's an exponential growth, y is equal to 4 to the x power. So as I look at this, what is my asymptote? What line am I approaching but never crossing? It's going to be this line right here at y equals 0. So we can divide by 4 as many times as we want, because that's what's happening when you have a negative exponent. And you're just going to keep getting smaller and smaller fractions, but you're never going to cross over 0. You're never going to be able to go to the other side of your axis there. Now, our domain, our inputs, what possible x values can I use? I can use all real numbers. What are the possible range, my possible y values that I get? Well, I just said we can't cross over to negative, so I know that y has to be greater than 0. And as you start to approach real world problems that we see in the last section of the notes here, you're going to have to start thinking about, well, in the context of this situation, does it make sense that it's all real numbers, or that y is going greater than 0 to infinity? Or is there a limit to where it can go based on the criteria I'm given? So you're going to have to think about that. So now as x decreases, as it goes towards negative infinity, right, as x goes this way, what is happening to my y values? My y values are approaching 0. And as my x values go towards positive infinity, what is happening? My y values increase. All right, they are going up. It's growing, 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 growing. All right. So now there's a U-try problem. We have an exponential decay problem. I'm already telling you that. And you have to figure out the asymptote, the domain, the range, and the end behavior for this function, y is equal to 1/3 to the x power. All right, so we're going to take a look at this. The asymptote, what line am I approaching but never crossing? It's going to be y is equal to 0. So we have a horizontal asymptote here. As you look at more complex equations, you may have a vertical asymptote as well. But for right now, we're only dealing with a horizontal one. Our domain is all real numbers. Any number I can substitute into that for x and take 1/3 to that power, and we will see what happens. We can get very small or very large numbers depending on what we're putting in there. Our range, again, y for this problem is greater than 0. We are above 0, and we will never equal 0. So it's going to be above 0, greater than. So now as x goes to negative infinity, as we're going in that direction, what is happening to our y values? Well, they increase. And as we go towards positive infinity, as we come this way, what's happening to our x values? They approach 0. And it helps if I'm on a pen tool. They approach 0. Now, for example 2 and 3, we've got some word problems, and we are going to break down some of the key features of the problem, and we are going to identify the relevant domain and range in the context. So, Sarah wants to crowdfund a film project. To spread the word, she shares the page with 3 friends and requests that each friend share it with 3 more friends. The function that models the number of new people given the link to the crowdfunding page Y, given the amount of cycles x, is defined by the function y equals 3 to the x power. Identify the key features of the function and identify the domain and the range in the context of this situation. All right, so we have our function and we have our task. Our function right here is y equals 3 to the x. So first of all, is this going to be exponential growth or decay? Well, I look at my base. The base is, what's below the exponent. My base is greater than 1, so this is exponential growth. Where does my asymptote fall? Well, we know that that's just going to be y equals 0. We're not shifting at all. We haven't taught you how to shift anything yet. We're not shifting, so it's just y equals 0. The domain, what does it make sense? What inputs, what x values can I use? Remember that x is the amount of cycles of passing out the link to her crowdfunding page. Can I have a negative number of cycles? Can I have negative people that I've talked to? No. So my x value has to be greater than or equal to 0, right? Because it's got to be 0 cycles would be she's given it to nobody. And what is her amount? Her amount would be 1, because it would be her. And then she multiplies that out by other people as she gives more cycles. My range values, my y values, what's going to happen? Well, I can't go below 0 because, right, y is my number of people, number of new people given the link, right? That's y. So it's always going to be greater than 0. Can I give the link to negative people? No, that doesn't make sense. So it's always going to be y is greater than 0. So as x goes to negative infinity, if it's exponential growth and we're going towards negative infinity, we are going to approach 0. And as x goes to positive infinity, y increases. It triples every time you add a new cycle in. All right, let's go look at letter B. The half-life of a substance describes how long it takes for the substance to deplete by half. The half-life of caffeine in the body of a healthy adult is approximately 5 hours, meaning it takes 5 hours for the body to break down half of the caffeine. Suppose an energy drink contains 160 milligrams of caffeine. The amount of caffeine Y left in your system after X hours is modeled by the function Y equals 160 times 1/2 to the X over 5 power. Identify each of the key features in the function and identify the relevant domain and range in the context. Well, if we are getting smaller every time, right, half of it is being depleted, that is exponential decay. And we also see that because we have a fraction that is less than 1 right there being raised to the power. Our asymptote is still going to be y equals 0. We can't cross over 0. We're not going to get to 0 caffeine. There's always going to be some minute trace of it. Okay, our domain for this one. So x is the number of hours after taking the caffeine. Can I have negative hours? No. So x is greater than or equal to 0. That's going to tell us how much we had when we started. All right. Now, our range values. What is my range going to be for this? Well, I know I can't be less than 0. So y has to be greater than or equal to 0. Or it has to be greater than 0. But here's the thing that we need to pay attention to. We only took 160 milligrams of caffeine. So our values for range has to be less than, actually not less than or greater than or equal. It's just greater than 0, right? So 0 is less than y, which is less than or equal to 160. So we have to be between 0 and 160 milligrams of caffeine in the body at any given point as the body is processing. As we go towards negative infinity, theoretically, your amount of caffeine would increase. So these end behaviors for infinity and negative infinity is really more theoretical than it is practical for one half of it. Now, for the other half of it, it does act practically because when x approaches infinity, positive infinity, y is going to approach 0. Because every 5 hours that goes by, half of that caffeine is gone. So you divide by 2, divide by 2, divide by 2, divide by 2. And eventually you're talking about fractions of a milligram, and you eventually get to a point where you can't even measure it. It becomes so small. Okay. So you guys are going to try letters C and D now on your own, and then I will go over them. So letter C, until 1972, a commonly used pesticide in the United States was DDT, which has a half-life of about 15 years. If a crop were sprayed with 200 grams of DDT, then the amount remaining y after x cycles of 15 years can be described by the function y equals 200 times 1/2 to the x power. Identify the domain, range, and end behavior of the function. So first of all, we're talking about things decreasing or decaying, so that's exponential decay. And our asymptote still is y equals 0, horizontal line at 0. Our domain, time cannot be negative, so our x values have to be greater than or equal to 0. We can't go backwards because now we're talking about before the crop was, the spray was applied. That doesn't make sense. So it's going to be greater than or equal to 0. Our range values, well, we know that we're decreasing towards 0. So we have 0 is going to be less than y, which is going to be less than or equal to 200. It's equal to 200 on the day that it was sprayed. And then from there forward, it is decreasing every single year. Regularly, it's losing it by half every 15 years. Okay, so now here we are 45 years later, and there is still DDT out there in the environment that is still causing effects. It was banned because it causes various cancers and birth defects, although it was an incredibly effective pesticide at the time. All right. Now, letter D. Suppose a wise young person asked their ruler to provide rice for their village. They asked for 1 grain of rice on the first day, 2 grains on the second day, 4 grains on the third day, and so on, doubling the amount of rice each day until the 30-day month ends. The function y equals 1/2 times 2 to the x models this situation where x is the day and y is the number of grains of rice. Identify the key features of the function and identify the relevant domain and range in the context of this situation. So this is all about delayed gratification, and this is an old fable of, asking for these grains of rice or asking for a single coin each time. But then as it multiplies out, you start to see the power of exponential growth, and you end up with incredibly high amounts of food or incredible wealth over time. So This is, we are multiplying by 2 to the x power. The base is 2, so this is exponential growth. Our asymptote remains at y equals 0, right? Our domain, well, we can't be negative in terms of days, so domain has to be greater than or equal to 0. What is my range? What are my outputs of this function? Well, on the first day, so day 0, right, we've got anything to the 0 power is 1. So it's weird, but okay. So we need to have, we're going to be greater than 0 because we can't actually get 0 grains of rice because on day number 1, we're starting with 1 grain of rice. All right, so y is going to be not equal to, y is going to be greater than 0. Now, what is the end behavior? As we approach negative infinity, it's exponential growth. So as we get closer and closer, or further and further to the left on the graph, we are approaching 0. And as we go towards positive infinity, y values are going to increase. And they're going to increase wildly. So let's just type this in, 0.5 times 2 to the 30th power. And that would give us, let's see, we're just going to write this in for fun. We've got 5, 3, 6, 8, 7, 0, 9, 1, 2. So as I break that out, that would be if you were to double the grains of rice every single day, starting with 1 grain on day 1. On day 30, you would receive 536,870,912 grains of rice. So we can see the power of exponential growth, even as small as a sample size of 30. Where do we see this in the real world practically? Viruses and population extrapolations often are mimicking, to an extent, an exponential function. So the early days of the COVID-19 pandemic, we were witnessing transmission rates of the virus that were approaching exponential levels, thus the concern about it at that time. So that's what we've got for our notes today. If you have any questions, bring them to class tomorrow. Otherwise, have a great day.